Okay, and now welcome back to the next content here. In the first um, overview introductory lecture, I spoke a lot about understanding the mistakes that people make, human error essentially. And obviously, there's a lot that we need to do to get into the causes of human error, and that relates to all of the applied psychology that I have already mentioned, right? Limits to human perceptual, motor, cognitive abilities. But before we get into that, there's something else that we can do, which is there's actually a little bit of research on the nature of errors themselves. And so we want to talk about ways that we can understand the kinds of errors that exist. So we'll start with that. So as noted here, I'm going to try to go through this relatively without too many tangents as I may have done in the first set of notes here. But I think we've already addressed this point here, right? So that we know that because people are prone to a variety of biases and limitations, they are going to make mistakes. We're not going to be able to prevent errors entirely, but we can at least minimize errors. But the only way to minimize errors is to understand why people make them in the first place. So let's start by talking about these kinds of errors, classifying error types. This may seem somewhat obvious, but maybe not, but it's worth making a note of the fact that some errors are intentional and others are unintentional. Now, we think unintentional is probably the obvious case, right? Everything that I think I've described so far in the previous, especially in the previous recording, uh, is about people doing things they did not intend to do. I spoke about World War II pilots confusing the controls for flaps and landing gear. That would certainly be an unintentional error, right? They did not intend to confuse those controls and activate one when they meant the other. Um, and so certainly we don't think of intentional errors very often, right? But people, in fact, do things quite intentionally all the time. Now, I have a fairly simple example here. Imagine a person working in a warehouse who has to transport a load, and they happen to have a 110-pound load that they need to transport somewhere. And they have a dolly that is designed and labeled even perhaps to support only 100 pounds. So our worker can now make a choice. One choice is to make two trips, right? And so put half or so of the 110-pound load on this dolly and transport it to wherever it has to go, and then go back and get the other half and make two trips. But on the other hand, perhaps this person says, well, I don't want to make two trips. And so I'm going to try to see if I can get by with overloading my cart by an extra 10 pounds. So this is an error. Now, the question is also then, well, does this error have costs associated with it? Is this going to lead to an actual negative outcome? And the answer to that is, well, maybe and maybe not. And so that's an issue here, is that a lot of times when people make mistakes, uh, there are no costs, right? That is, nothing bad happens. And so that's maybe even something else to think about too, which is perhaps sometimes people will become complacent because they have performed these intentional errors repeatedly, and nothing has so far happened, which leads them to believe that perhaps it's perfectly safe to do something such as overload this cart. And one day it may turn out to not be safe, right? So that's an intentional error, right? You're doing something that you know is not really supposed to happen, but you, for whatever reason, whether because it's you believe it's safe to do because of past experience or what someone else has said to you, or whether it's simply just because you're in a hurry or otherwise don't feel like following all of the safety protocols that you are expected to follow. And so you have these intentional errors. Now, at the bottom, I mentioned the costs, right? So some errors, as noted, may have no costs, but some can be catastrophic, right? In the sense that now we could be looking at loss of life or significant injury. We might also talk about the ability to recover from an error, right? So If we think about my unintentional error example of accidentally turning off the headlights when you are trying to activate the windshield wiper, that's a recoverable error, right? You would immediately realize, well, oops, I just turned off my headlights, and you would correct that action by turning the headlights back on, and hopefully nothing terrible would happen, right? Maybe if it's dark, you're on the road that you're driving on, you might have a small interval of time where you're driving without being able to see the road effectively, but maybe there's a good chance that nothing bad is going to happen in that one interval, and you get the headlights back on in time before you drive off the road or anything like that, right? So that would be a no cost but recovered error, perhaps, right? Obviously, something bad might happen. What if a person, in doing so, panics after having accidentally turned off their headlights, and then they, in their panic, they swerve off the road and crash. So in that case, they fail to recover their error. So there may be psychological issues like that that might determine whether an error can be recovered or not. But sometimes errors are unrecoverable for other reasons. So for example, there's one example comes to mind randomly. I don't know why. I'm thinking of what I've read about fighter jets in the past, and the idea is that when you are making a heavy heavy bank, a hard turn in a fighter jet, uh, it's one thing that you turn the essentially the steering wheel. It's not really a wheel, right? But it's a stick that that causes this bank to occur. But one of the things that you have to do is you have to simultaneously turn the stick to the side while also pulling back on the stick a little bit, because pulling back is actually how you climb elevation. And what happens is when you do a hard bank like that, the plane will lose elevation. And so you have to account for that and compensate for that by pulling up on the stick while also banking. And if you don't do that, you will lose altitude. And there are certain dangerous maneuvers when, if you perform a bank at a very low altitude, um, there's considered to be essentially what's called a floor, right? The idea is that you cannot perform these maneuvers at too low of an altitude, because the plane will drop its altitude a little bit, and there's nothing you can do about it. Uh, and so if you don't get this done correctly or at the sufficient altitude, you're guaranteed of crashing at this point, right? And it cannot be recovered because the plane is already uh, too low to recover from this maneuver. So there's all kinds of situations like that in transportation, for example, right, where you've essentially set things in motion by committing this error, and there's nothing to be done to stop it from happening. Other ways that we might classify errors here, I said a second ago that you commit an error, right? Well, that's one example. That's our second list here, right? So our worker who overloads their dolly has committed an error, and our driver who has selected the wrong control who has committed an error. But there are sometimes errors of omission. We skip steps quite a lot, right? This can be kind of a classic thing. Another example here is changing the tire on a car, because there are certain steps that you have to do. A good example is that it's quite helpful to loosen the lug nuts on the damaged tire before you use the jack to lift the wheel off the ground. Because of course, once you lift it off the ground and then you start trying to turn the lug nuts, you're going to spin the wheel rather than spin the nut. And so if you do this in the wrong order, we could say that's a sequential error. Actually, I should probably consider it in that sense, right? But we can think of it as an error of omission because you skipped the step. But there could be various other examples where you skip a step, like maybe in cooking, for example, if you forget to add an ingredient, and then you go straight to putting everything in the oven, and then it's only afterwards that you realize, oh no, I forgot this ingredient. Then of course it's a bit too late for that, right? So that would have been an error of omission, where my example about changing the tire and doing things in the wrong order is a sequential error. So let's be straight on that. Or an extraneous act, right? So there might be situations where in the middle of doing one particular task, you perform an extraneous action, meaning another action entirely that has nothing at all to do with the task at hand. And that distraction could be something that causes an error. Here is a very, very paradigmatic example of distracted driving, right? When driving, all of the driving specific tasks would be considered the essential things, right? Steering the car, lane maintenance, speed maintenance, monitoring hazards in terms of what's in front of you and what's in your mirrors and so forth. And adding in cell phones and technology of various types would be all considered extraneous acts. Eating, another example, right? Uh, all extraneous acts that can increase possibility of an error. And lastly, time errors, right? Sometimes we have to perform complex tasks that must be done with very specific timing. Uh, for we could think of being in a band and playing music is one example, one simple example of that. And obviously, if it's your time to come in and play a certain musical note and you are late, then you've made an error, and that's a time error, right? But there could be all kinds of different situations. Surgery probably is a good example of time errors, right? That there might be certain things that have to be done within specific time constraints while a patient is under anesthesia, for example. And so not fitting within those time constraints would be time errors. One thing that we can also try to do here when understanding errors is try to predict the probability of an error. And this sounds really good in principle. We could do such a thing, but humans are notoriously unpredictable. So it's not necessarily as concrete of a thing as we might imagine it, but at least we have some in principle things that we can work on here. So we're going to define the probability of an error as P. Now, probabilities can only go up to 1. So if the probability of an error is 100%, that is, it is definitely going to happen, then our P is 1. The opposite, or I should say inverse of that, is 1 minus the probability. So that's called reliability. And so a perfectly reliable human is a person who never makes mistakes. And so, of course, we know that that's not true. So when we have a 100% chance of error, we have a 0% chance of reliability, right? And so if we have a 99% error likelihood, then we have a 1% chance of reliability, right? So what we want to know here is, can we possibly calculate P, or inversely 1 minus P, right? Well, what that means is that what we need to do is, again, I've used this phrase in the previous set of notes, a task analysis. So we want to subdivide what a person is doing and the task that a person is doing into a series of steps. So I mentioned driving a minute ago. So we can think about a task analysis for driving means that you have to look at your speedometer, and you have to be able to see the indicated speed of travel that your car is at. You also have to be able to look at the speed limit signs on the roadway. You have to also remember the speed limit signs after you have looked at them and passed them. And then you have to compare the indicated speed in your speedometer to your memory of the speed limit and evaluate whether you are traveling too fast, too slow, or just right speed. And then once you make this determination, you have to select a response. Should I accelerate and get back up to speed because I'm going too slow? Should I let off the gas a little because I'm going too fast? Should I just maintain my current state? So as you can see, when we do a task analysis, what we're doing is we've taken that one thing, one aspect of driving, speed maintenance, and we're going to break it down into very, very detailed steps, right? What do I have to do? What information do I need in order to do it? what are my choices and responses, and how do I perform them? And that's another thing, right? When it comes to if I speed up or if I slow down, how much pressure do I have to apply to the gas pedal in the car? So there's a lot of little granular details that all have to be accounted for here. And there's a chance now of a mistake at every step of the way. Is it possible that I misread the speedometer? Is it possible that I misread the speed limit? Is it possible that I missed a speed limit sign in which the speed limit has changed in the last few miles? Is it possible that I have forgotten what the speed limit was? Is it possible that I am somehow misjudging whether I'm going too fast or too slow? Maybe I am going too fast because I'm going to make an intentional error here that I think I can get away with going 10 miles an hour over the speed limit or 15 miles an hour over the speed limit, and there won't be any negative consequences. Another classic example of people who make intentional errors are people who intentionally go over the speed limit. Many, many times this leads to no consequences, right? We don't get pulled over, we don't get caught, we don't get into an accident, and we think, well, it must be fine, except of course until it's not fine, and sometimes it leads to consequences. And so we see that with the chance of making a mistake at any one of these steps, we have to determine what is the possibility or probability, better, that any one of those steps could involve an error. And I have to estimate the probability of that error individually for each part of the step. And then I have to think about now the sort of overall probability of an error occurring at any one of these possible steps, right? So we're looking at things like conditional probabilities and conjunctive probabilities and so forth. So it gets fairly complicated right off the bat in order to predict an error here. And that's not to mention the fact that that's just one aspect of driving, right? We also have to think about hazard monitoring and lane maintenance as well, and monitoring where I am in the lane and making adjustments with the steering wheel. So again, we can imagine that actual calculation of error probability and reliability of a driver can become fairly complex, but at least in principle, this is what we're doing, right? And I hope that's clear that what we're going to do is we're going to subdivide these tasks into these very granular details, every little step of the way that has to be where some piece of information has to be detected and a response has to be performed. And there's possibility of error at each one of these. Wherever we can identify the likelihood of an error, we can also try to do something to ameliorate that. So for example, one error that I mentioned was the issue of, is it possible that I misperceive the speed of the car, that I misperceive the speedometer in some respect? Well, what I want to do is I want to evaluate things like what kinds of visual ability is needed to read the speedometer. And we're going to maybe think about that a little bit when we get to the chapter on vision in a little while. But the idea is that we could think about human visual limitations and design speedometers and other aspects of your car's dash display to ensure that visibility is maximized, right? So that there's little chance of someone misperceiving their current speed. With the placement of speed limit signs on the roadway, there's not much that we can do there. It might be nice, for example, we can imagine technology improving the situation a little bit, because currently, speed limit signs are spaced out on roadways at some interval that I couldn't quite quote to you exactly what the rule is on that. But presumably there's some reasonably good, I should hope, reasonably good guidance on the spacing of these signs. Not to mention the size and readability of the signs. Usually that's pretty well worked out. But, we do have within the realm of imagination the possibility of technology assistance here. We could have GPS embedded into cars that keep track of where the car is, right? What road is it on? And that could be combined with a database of known speed limit settings for all of these roadways. And that could then be displayed inside the car somehow, right? That could be displayed on the dashboard next to the speedometer so that you could always have access. You would not have to wait to see the speed limit sign. your car would tell you what speed limit of the road that you're on because of technology assistance here. Now that is possibly worrisome as well, because it might be the case that you might get confused, and when you look at the indicator in your dashboard that displays current speed limits, you might think that that's your current speed, and maybe you get confused here. So if we were going to have such a system, it would be very useful to ensure that presentation of the current speed limit of the road that you're on is easily distinct from the indicator that displays your car's current speed. But again, these are things where we think, yeah, we can maybe try to minimize errors if we think that there's a high increased risk of error because of speed limit signs being too sparsely spaced out on the road, or occasionally just missed because you happen to be looking elsewhere. Then embedding that information into a GPS and car navigation system would be pretty useful. So what I have done here is I've described exactly what it is we're trying to do. We are trying to do a task analysis. And what we need to do when we do a task analysis is to always think about the user, right? It's not just about getting the task down to all these granular little steps, but also at each point of the way, where does the user fit into this? And how might they make a mistake, and why would that happen? What kind of human issue would cause this to occur here? So one example here, to move away from driving, perhaps we have somebody who has to monitor gauges for some industrial workplace setting, right? Maybe gauges that indicate the pressure in some sort of a pipe system that handles high pressure steam or something along that line. And so what we're going to do is we need to intermittently check those numbers to make sure that everything remains within spec. So every time, of course, that our operator looks at the gauge is an opportunity to make a mistake. And since these gauges have been placed directly overhead for whatever reason, right, depending on just who designed the layout of this industrial plant setting here, they decided to put gauges in some weird location on the ceiling. So now our person has to look up, right? And is it possible that looking up causes one to not always have a good view of these monitors, right? So that leads to the possibility of some mistake here, and we might be able to know why. And of course, maybe because those gauges are located in such an unusual position that our operator forgets to look up, or because of the inconvenience and neck strain, they put off looking up at those dials, and therefore they kind of maybe don't check those values as often as they should. So there's another issue here. It's not just the act of looking, an act of commission that involves misreading the gauge, but an act of omission or a time error, right? So the act of omission is simply just not looking at the dial because you just don't want to, because it's too much of a strain on your neck, or you're not checking often enough, which might be a time error. Here we have a person who has to remember numbers as well. Maybe the idea is that some system gives you a series of numbers that you have to then go type in on a keypad somewhere. And, there's some value. This happens a lot, for example, nowadays when you get like, you're logging into a system and you get texted an authorization code. It's usually a 6 or 7 digit number. Now, a lot of times these systems bypass memory issues because phones are smart enough now to copy those codes into I'm losing the term here, but the little memory storage buffer for copying and pasting into the authorization screen of whatever app you're logging into. It's going to drive me crazy now that I forgot this simple old computer term for where the memory goes, where things go when you copy and paste. But the idea, speaking of memory issues, right, is that if the phone wasn't helpful here, right? If the phone wasn't going to save that, then you would have to look at your text message and briefly memorize the 6-digit code and then switch back over to the app that you're logging in and type that 6-digit code in, and you could possibly make an error here. And, again, is the cost of this error severe? Well, maybe, how time sensitive is it that you get logged into this app? If it's a very time sensitive issue, then maybe there's something going on here. And again, operating controls here that a person has to turn a valve and then run 12 feet to open another one, and it has to be done within a certain amount of time. So there's a risk of a time error here, but can the person run fast enough to do that, right? So we have to think about, again, all of the steps involved in all of these. Detailing at the very granular level, turn this knob, by exerting a certain amount of force, and clipboard. This randomly happened in my thing. The clipboard is the place in the computer that holds things that you've copied, right? Turn the knob by exerting a certain amount of force on that control wheel, and then travel to this other valve that has a control wheel on it within X period of time by walking, and that means you have to walk at some rate, how many steps per second, and then turn this knob a certain direction by exerting a certain amount of rotational force with your wrist. And so we have to think about that, does the person have enough strength in their arm to exert that rotational force? Do they have the mobility to walk that distance in the sufficient amount of time? And so each one of these is a step that contains a risk for an error. Simple, not so simple example, but a classic example of a task that may require a lot of breakdown in terms of task analysis and complexity here, and has a high risk of error. This is the control room of a nuclear power plant. So what we see is we have lots and lots of displays, monitors, gauges that perhaps convey very important system states, right? Pressure and temperature of the reactor and things of this nature. We have controls that do various things, and that maybe sometimes you have to operate these controls to ensure something happens or doesn't happen. The risk of an error, is at every step along the way. You have to obtain information when faced with a massive amount of information. So you have to have knowledge and training to direct your attention at the appropriate display at the appropriate time without forgetting to look at other things, right? So there's issues here of sequence, of time, forgetting to do something as an act of omission because you forgot to look at one thing and get one piece of information, or to turn one knob, or to flip a switch. So there is a great variety of tasks that have to be performed here with some degree of complexity, and there's a high risk of error. And then think about consequences of error here. You don't want to have a nuclear meltdown at the nuclear power plant, right? So obviously, to the extent that we could try to simplify such systems so that they are not like this, right? Or we want better trained operators than Homer. But the point being is that maybe to some extent there are certain limits because of the complexity of how a nuclear power plant works, that we can't just simplify the controls to something that any regular person could do. So we may need to have the highly specialized trained engineers operating these plants. Now, if we can try to quantify errors, calculating error probability, well, one thing we can also do is we can also, instead of trying to predict the probability of an error based on how likely we think it is something could happen after doing a task analysis, we could simply just measure and observe errors as they occur, right? So what we can do is that we have a task, it's already being performed by a person. And now what we have to do is we're going to try to determine how many mistakes they make and use that to calculate their error rates and their error probabilities, right? So human error probability here is defined as how many mistakes or errors a person makes given a certain number of opportunities for making errors, right? So we have to determine how many opportunities for errors there were versus how many mistakes they truly did make. So here's one fairly basic example, right? Somebody is employed as a quality control inspector, QC inspector, for ball bearings. Now, I'm sure we don't, in places that manufacture ball bearings, I'm sure they don't have to rely completely on a human to inspect ball bearings, right? So what we want to do is we want to make sure that they're not out of round, right? So we want ball bearings to be as close to perfectly spherical as we can get them. But every now and then, you're going to have some that are a little lopsided, and therefore they're out of round. Um, and so maybe we have a way to do this. Maybe we can let them spin down into a little cone-shaped funnel. And as they roll through the cone, anyone that's out of round is going to have a clear wobble in its path and its trajectory, right? So a person would have to stand over this thing and look for any ball bearings as they come out of some chute and they start rolling down this funnel, to look for any wobbles, right? And if you see one that's wobbling, you got to reach down there and grab it. This is probably not a great system, right? Let's say that a person does this 5,000 times. So there's 5,000 ball bearings that are going to come through their little funnel system here, and they have to monitor. For some reason, let's imagine that we know that 1,000 of these ball bearings are bad. It's probably not a good manufacturing system if 1 out of every 5 of the things that you produce are somehow defective. But let's just say that we possibly may know this and that that's what the numbers are. But instead of having identified all 1,000 bad ball bearings, our inspector has only found 400, and that means they've let 600 out of round ball bearings through. And that means that they have now made 600 errors, right? So we can simply calculate the error probability here as 600 divided by 5,000, right? 600 actual errors divided by 5,000 chances, and we get an error probability of 0.12. Essentially, they've made a mistake 12% of the time. Although this is only half of the picture a little bit, because one thing that this kind of assumes that of the 400 bad bearings that our inspector has removed from this funnel, that those were all correct identifications of bad ball bearings. And so that the only mistake they have made is letting 600 bearings go through, calling them good. But isn't it also possible that sometimes when you pull a bad defective item from the assembly line here, that could also be a mistake, because it's possible that it was really a good ball bearing and it was rolling true, and you simply just misperceived its trajectory, thought you saw a wobble, but there was no wobble. And so you've actually pulled a good bearing out instead of a bad one. So there's other kinds of errors. We're going to have to get into that a little bit later in these notes here, but just the basics of it here is that this person has made errors on 12% of their opportunities. So one thing we might want to ask at this point is that good or bad? And well, do we have a standard? And well, the answer is that kind of not really, but it depends. There is a whole field known as Six Sigma. And the idea is that this is a way of trying to evaluate reliability in any kind of process or system. And it's used to determine the kinds of error rates that would be considered ideal, right? And so according to the Six Sigma model, we want our error rate to be 3.4 per million opportunities, 3.4 errors per million. So that means out of every million opportunities for an error, only 3 plus maybe 0.4 will have been actual errors, right? And we can then turn that into, our p-value, 0.00034, right? So obviously the P of 0.12 is much higher than the limits allowed under Six Sigma. So those are pretty stringent standards. And if we're going to follow that kind of stringent standard, then that means we need to identify where the errors occur so that we really can minimize them as much as we can. Now, I just got done saying that our inspector, our QC inspector, might commit two different kinds of errors, right? One is an error that we're going to call a miss, right? The miss is the fact that there was a bad ball bearing that they missed and they let it go through, treating it as if it was actually okay. But the other kind of error is called a false alarm. And this is the one where they think that the bearing is bad, but it's actually good. So they have essentially said that one, there's a problem here, but there's not really a problem. It's kind of like a false alarm when we say that, oh, if I pull a fire alarm because I think there's a fire, I said, yes, there's something bad here. But if there was no fire, then that was a false alarm, right? Whereas a miss would be buildings on fire, but I somehow don't notice that and therefore fail to pull the fire alarm, right? So both of these are errors, right? So what we need to do in order to understand these kinds of errors and what makes a person likely to perhaps commit certain misses of certain important signals, or maybe have false alarms about certain kinds of signals, we want to employ another psychological theory called signal detection theory. And that's what these are. These are signals that we have to detect. Maintaining the speed in your car, that means you have to detect the current speed of the car, and that's a signal that comes from your speedometer, and hopefully that's a signal that is easy to detect. You also have to track the speed limit on the road, and again, that's a signal that you have to detect. Our QC inspector, who has to identify bad ball bearings by detecting a wobble as they roll down a funnel, is another signal that that person has to detect. And so our question now is what determines their ability to detect the signal? One of them is what we're going to call sensitivity. This kind of research has really just sort of bloomed out of what's known as psychophysical testing in human sensory research. And so a typical example that I think most people would have experienced in their life is getting a hearing test, right? So if you go to an audiologist and you put on the headphones and they play little tones through the headphones, and you have to provide a response like raise your hand or press a button when you have heard the tone, they're concerned about your sensitivity, right? They want to know if you can hear certain very faint tones. And so when you say, yes, there was a tone and that was correct, right? Then we'd say that, yes, you detected the signal, right? But sometimes they present a signal and you don't detect it because maybe there's damage to your ears. And therefore the tone was not strong enough, right? So we have a loss of sensitivity here because the tone was weak, the signal was weak, and it was not strong enough to activate the receptors in your ears because of perhaps some damage to your hearing. But one of the things we also need to realize is that in the real world, stimuli are not presented in such perfect, ideal, isolated conditions, such as isolated tones played over headphones in an otherwise quiet background. A lot of our signals occur in situations that are noisy. So if you are in a crowded environment, such as, let's say you work in a hospital and there's lots of bustling activity going on, but you have to make sure that you hear certain warning tones that might come from machines that are, maybe monitoring patients who are in critical condition. That's a signal that you need to detect. And so, of course, we can determine if it's loud enough for you to hear. But separate from that is if there's a whole bunch of other stuff happening and a bunch of other noise happening in this environment, is the signal for that one critical machine loud enough in relation to all of the background noise? And so that's what we're going to call our signal to noise ratio. And that is another factor that determines your sensitivity to that particular signal, is how much does it stand out from the background? Because if it's technically loud enough to be heard in isolation, but in noise, it just kind of blends in with the rest of the noise, then we would say the signal to noise ratio is low and you are less likely to detect it, right? You're not going to be very sensitive to that signal. So sensitivity and signal to noise ratio are certainly, of course, big important parts of our ability to correctly detect signals when they occur. But there's also something else going on here, which is considered to be a response bias. What's going to happen is that a person might have a certain tendency to say, yes, the signal is present, or no, the signal is not present on any given trial. Let's go back to our ball bearing inspector. Let's say, for example, that they have let 600 bad ball bearings go through, right? So they've made these 600 out of 5,000 errors, 12% error rate. And now they get in trouble, right? So management discovers how many bad ball bearings have passed this inspector. And certainly they want their inspectors to do a little better job. So they come back and they yell at this person and they're like, you're sending out all of these bad products to our customers, and our customers are complaining, and you're giving us a bad reputation as a company that makes defective products. You need to do a better job of identifying bad ball bearings. So that person is going to say, oh, I need to start identifying more signals, right? So this feedback, this criticism that they've received from their boss doesn't necessarily improve their sensitivity to detecting a wobble in how these balls roll down the funnel, right? They otherwise haven't necessarily done anything to make that wobble easier to detect by improving the signal to noise ratio or anything like that. They simply just have yelled at this person, which might bias their behavior and change their behavior in a certain way. And what this might do is causes them to increase their rate of saying, that's a bad one, that's a bad one. So now as they start identifying more and more bad ball bearings, presumably now they're not going to let those 600 bad ones go through anymore. But this tendency to just say that one's bad, that one's bad, that one's bad, more and more and more, might cause those false alarms to increase as well. So as they start pulling more actual bad ball bearings off of the assembly line, this might also increase their likelihood of removing some good ones as well. And then what's going to happen is they're going to get in trouble all over again, because once they start removing more of the good ball bearings, that might increase their what's called waste, right? Now all of those good ball bearings have been taken out of production and perhaps even destroyed at that point. And now there's not very many actual ball bearings left to be sold to the customers. And now management comes back saying, hey, you're throwing away all of our product. What are you doing? Stop throwing away all of our product. So of course, now that's contradictory advice. And our inspector goes back to letting more stuff go through. And then they get in trouble the next month for having too many defective products. And then they get fired, perhaps, right? So what we need to do is, not so worry so much about our inspector here, but maybe make that a better process altogether. But we can classify these choices that the person makes here. So if we say that the signal is present, let's say the signal is a bad ball bearing, then, and the user says, yes, that is in fact a bad ball bearing, we call that a hit. They have detected the signal when it was in fact present. And so that's a correct decision, right? It's like saying, yes, there's a fire, so I pulled the fire alarm. That was a hit. I detected something that was really happening, and I have a correct decision here. And if the signal is present, but I say it's fine, right? Nothing's happening when maybe the ball bearing really is bad, but I don't see it. We're going to call that a miss, right? So that's what we had with our 600 misses for the QC inspector. That's an error, right? So what determines the relationship between hits and misses? Well, it could simply just be that if the signal to noise ratio is very, very high, we're going to have a higher hit rate. And if the signal to noise ratio is very, very low, maybe we're going to have more misses, right? But what we can also see, though, is that if we do something such as bias our inspector to cause them to have more hits, to say yes more often, right? We want them to pull more of those defective products off, then they're going to say yes more often, right? So now what we're seeing is that on the side of this little 2x2 matrix here, if we do something to bias our subject here to cause them to say yes more and more and more because we want to have more hits and fewer misses, by saying yes more often, it also tends to increase not just the hit rate, but it also is going to increase the false alarm rate, which means that sometimes they're going to say, yes, this is a defective product when it was not, and therefore the signal was absent, but they said it was there, and that's called a false alarm, and that's an error. So we see here that separate from the signal to noise ratio, simply a bias towards saying yes more often will increase hits, but it will also increase false alarms. If we do the converse and we bias our person to say no more often, what we're going to do is we're going to increase the miss rate, but we also increase our correct rejections. And those are actual correct choices as well. So a correct rejection is when I say there's nothing, no problems here. There's no problems here. And in fact, that's true. There is no signal, right? So that's a good ball bearing. And in fact, it is, right? So those are correct rejections in the sense that I am saying that's not a signal. It's not a mistake. My job here is to detect mistakes. And I'm saying that that's, so the presence of a mistake is my signal. And so whenever I say, yes, the signal is there, the mistake is there, and I'm correct, that's a hit. Whenever I say, no, the mistake is not there, and it's not there, that's a correct rejection. Those are both correct responses. But whenever I say, yes, the signal is present, but it was really not, the mistake, this was a bad product when it was really not, that's a false alarm. And when I say this is a perfectly fine product, no mistake, but it really was, that's a miss. So what we want to do is try to maximize our hits and minimize hits and correct rejections, right, while minimizing false alarms and misses. So how do we do that? Well, the first thing is we need to maximize our signal to noise ratio, right? That's going to drive up our hit rate. And the bias, on the other hand, is something else that's harder to determine is ideal, but over time we might be able to optimize that kind of responding a little bit. Now, if we're told that we made a mistake, what do we do about that? Well, there's not a lot of research on this, to be honest. This is a very old study, as you can see, from Rabbit and Rogers, but back in 1977. And what they did in this situation is they had people performing a simple reaction time task. That's what the RT stands for. Choice RT, what is that? I actually have a little more detail in several future chapters about choice reaction time. But what we have to do is, let's imagine a situation where there are different numbers that can appear on a screen, right? Odd numbers and even numbers. And if it's an even number, you press a button with your left hand. And if it's an odd number, you press a button with your right hand. And so your task is to sit here and to stare at the screen and monitor these numbers and perform the appropriate response. Now, this is a fairly simple task, but you're told to do it as quick as you can. So you have an instruction here that you have to try to do this as fast as you can, right? Every time a new number appears on screen, you got to press this button quickly, but you're still supposed to hit the right button as well. So you have to be fast and accurate. And if you get it right, nothing happens. But if you get it wrong, maybe there's going to be this kind of a warning buzzer, like right? So that was wrong. So then what happens is that when you get this feedback that tells you that you have performed the incorrect response, and it doesn't always have to be like one of those, annoying warning things where you get the, but you simply, sometimes we know when we've made the mistake, that because there's very little ambiguity here, I know it was an even number, so I was supposed to hit the button with my left hand, but somehow my wires got crossed and I just went with my right hand instead because, my hands just didn't obey. I'm going too fast and I exceeded my ability and so forth, right? So in one way or another, we know that we have made a mistake. And as it turns out, what Rabbit and Rogers discovered is that as soon as a person makes a mistake in this task, occurs randomly, kind of spontaneously sometimes, right? They noticed that these errors would cluster together, right? So what would happen is that a person makes one mistake, and that means that on the very next trial, so that's the E+1 trial. So there's trial E, which is the error trial, but the very next trial is E+1. There is a hugely increased risk of there being a mistake on the E+1 trial. But what also is the case is that there's a very increased likelihood that the response on the E+1 trial was the response that was supposed to be performed on the previous error trial. So this is called perseveration of errors, right? Because what happens is that because I kind of catch myself making an error here, that now I remember, oh, I was supposed to do this. And so in the very next trial, I'm more likely to do this when maybe I'm not supposed to do that and I'm supposed to do something else. And so you see that clustering of errors and perseveration of errors. And then, of course, after a minute, after a few trials, the person kind of gets themselves back on track, and then they're going to have a longer string of correct responses until another spontaneous error. And again, you might see a little clustering of errors again. So this fact that making one mistake increases our likelihood of making more mistakes is kind of an interesting phenomenon that we possibly also want to account for as well. Correcting errors can only occur when an error is recoverable, right? We mentioned the issue of a recoverable versus non-recoverable error previously. So some errors are simply just non-recoverable. I guess our plane crash here is a non-recoverable error. Although the caption here with the joke is that we learned from it and we'll do better next time. But next time means the next time we build a plane with better wings, right? But more to the point here, we can only recover errors and correct errors when we are aware that we have made them. And so that we need that feedback. So as I said, with the Rabbit and Roger studies, there can be versions of this where we actually play that little warning tone that tells you you have made a mistake. And that's that infamous sound that nobody likes, because every time you hear it, that's an immediate cue to say, I did something wrong, got to fix it perhaps, right? So keeping the user in the loop is the phrase here. User in the loop means that we are always aware of what's happening, right? We know what we have done, we know what the system is doing, and we know when we've done the right thing and we know when we've done the wrong thing. But it's more than that. It's more than simply just knowing that you have made an error. You need to know what kind of an error. That is, what is it that you did that was wrong? What should you have done? And what do you need to do to fix it, right? So it's one thing to simply be aware of the error, but we need to know what was the error and how can I fix it? What's the solution, right? And so these are all very important things as well. That means the system has to provide this information, right? This, instead of just beeping at you, bang, wrong, right, bang, wrong. We need better information, right? I had this kind of stuff in the first set of notes, right? Some of these old dialog boxes from computers here. Can't open a website, operation aborted, but so there's an error here, and I know now the error occurred, right? This is clearly a big red circle with the X there. So that all seems to indicate something has gone wrong. Is it my error? I don't know. And I don't even know what to do about it, right? It just says operation aborted. I can't do whatever it is that I want to do. Again, we're trying to update something and we're aborting that procedure because of some ACP state failure. If you don't know what that is, then you would have little idea how you can, what it means, what has actually gone wrong, and what you could try to do to fix it. The infamous one, if you've never seen the movie Office Space, which is about 25 years old or so by now, it is got some good human factors plus IO psychology humor, as well as just a good funny movie. But PC load letter, what does it mean, right? This is if you don't know what this means, I don't think printers use these kind of messages anymore. We've finally gotten smarter about this, but for a good chunk of the 90s and early 2000s, if a printer ran out of paper, the code for that was PC load letter, right? Now, why not just say paper tray empty or add more paper or something like that? Those would be much more meaningful error codes, but whoever designed the original codes somehow thought PC load letter was the appropriate message to give to users. And for a lot of frustrated people who were the first adopters of standard office computers with printers, this was the bane of many people's existence, as well as maybe something as terrible as this. This is the BSOD, short for the blue screen of death, right? Meaning that in Windows, your computer has crashed. in a particularly bad way. We have some code here that we don't know what means, and we got some instructions here, right? Press any key, press Control Alt Delete, and so forth. But not a lot of choices and not a lot of explanation as to what has gone on here, right? So not a horrible error message, but certainly not as helpful. Well, we just have a few humorous examples of things. And oh, it's so early days of Apple Macintosh computers. You can see maybe they made some effort here at providing more meaningful error messages here, right? So when there is a low battery on your on the wireless mouse in this case, you don't just see the mouse kind of flashing and shut itself off, right? You get a message that explains in plain language exactly what has happened and what's going to happen if you don't correct your error, and in specific instructions about what to do. And then, of course, by hitting OK, there's a kind of a forcing of an acknowledgement of that, that you have read that. As of course, sometimes people will just reflexively click those OK buttons without fully reading the entire message. And then you think, oh, shoot, no, I want to read that. Can I make that come back? And how do you make those messages come back? And that's not always an obvious thing that you can do. And the same in this case where somebody's trying to save a file onto a disk that doesn't have any more room left on it. So again, some very clear, plain language explanations as to what to do here. Although, here's a curious one. Is there any difference between hitting OK and hitting cancel in terms of what's actually going to happen after you have read and closed this particular message? And the answer is no. So it's not clear why they included both those choices when neither one has any. It's not like hitting cancel will cancel out the error and make it save, right? So not going to happen, right? This is the kind of thing that occurs when we really fail to eliminate errors. And I'm sure there have been any number of IT professionals who have had to do something like this, where a system just keeps breaking and they're the only ones who can kind of figure out how to fix it. And they have to put this kind of message on a screen that gets displayed to the users to just, if this keeps happening and this doesn't work, just call me and I'm going to have to come and fix it, right? So to wrap this up, we want to talk about trying to change the design of a system to minimize the errors, right? So there are things that we can do, for example, to maybe sometimes just make errors go away entirely. Exclusion design is what this is called. So we're just going to take that feature out. We're just like, this is a thing that's going to keep breaking. We're just going to get rid of it if we can, right? But can we do that? My example here is something that you may not have ever heard of before. So on really, really old cars, like the old Ford Model Ts and stuff like that from the 1920s, in order to start them, you have to turn the crankshaft by hand. So there's an actual lever crank handle on the front of the engine, and you have to perform a series of steps. And actually getting these things started was a little complicated. You have to kind of turn the ignition to off and then open the choke and then go crank it a few times to prime the engine and then go back and turn the ignition to on and close the choke halfway and then go back and crank it until it cranks up. And this crankshaft handle at the front of the engine is literally connected to the crankshaft of the engine. So as soon as that engine starts to spin and the crankshaft spins, the handle would spin too, except they have a mechanism set so that it automatically releases as soon as the engine turns over and the crankshaft starts to spin. So this thing doesn't take your arm off, right? Because you'd be holding on to it with your hand and you're turning it like this. I know you can't really see me here, but you'd be cranking it by hand. But what would happen sometimes is that the engine will backfire when trying to start. And the backfire sometimes causes the crankshaft to spin the opposite direction. And this automatic release on these hand crank starters doesn't work when the engine backfires. And so notoriously what would happen is that sometimes people would get their hand caught on this thing and it would spin around really fast and it would break their wrist or spin around and hit them in the arm and break their arm. Or sometimes it would hit people in the head and knock them unconscious. People have been killed by these things as well. So these old hand crank starting things that you find on old cars or even old tractors were quite dangerous. And lots of people were severely injured by them. Nowadays, we don't have to do that because there is an electrical coil inside of your car that spins the crankshaft up for you. And you don't have to worry about this kind of thing anymore. So that was an example of exclusion design, right? Is making people spin up the crankshaft by hand was dangerous. And in order to stop this from happening, we're going to come up with a completely new solution to starting cars, right? Another example we could think of now is possibly self-driving cars, right? They're not quite where we want them to be, but the idea is people are bad drivers. That's just the reality of it, right? People make all kinds of errors when driving and cause crashes all the time, every day. And if we could design self-driving cars that don't crash at all, right? If we could get it to that level, that would be a case of exclusion design, that we're simply just going to say nobody drives anymore. Computers and AI is going to take over this test for you. Now, if we can't get to exclusion design, maybe we try to just prevent the design through other barriers to prevent the error, through other barriers to errors, right? So repetition is one example, right? So if you have to do something two or three times in a row in order for an action to take effect, then that means that, let's say, for example, well, here's an example. When you delete a file on your computer, you could drag it to the recycle bin or the trash bin on the desktop of your computer. Now that is how we think of as throwing things away, and therefore maybe that's how we think of as deleting that file. But technically, the file still exists on your computer. And in fact, you can recover things from the trash bin at any time. You can open up the trash bin and pull those files back out of there and put them wherever you want to go, right? And you've now saved them and recovered them because you put that into the trash and then you thought, oh, oops, no, I really didn't want to throw that away, so I can go back and get it, right? Now there's a second thing you can do, which is that you can right-click on the trash bin and say, empty the trash, right? And that then removes these files from the trash bin so that now they are no longer really recoverable. Well, except they kind of are, because simply just telling the computer that you want to delete this file doesn't mean that the computer actually identifies the space on the hard drive where that file is stored and removes the data. The data is still there. It's just basically keeping a record of saying, okay, the user no longer wants this file, so that means these locations on the hard drive where that was stored are now freed up so that we can use them for other save files later in the future, right? So that means technically the file could still be there and all the data for that file could still be there. And there are certain specialized programs that you can run to get those files back, right? Even after you have not just dragged them to the trash, but even hit empty trash on that, right? So that means there's multiple steps here before a file is actually really deleted. And so that means that there's always a chance that because of this kind of barrier to really making things disappear, there's enough redundancy that you could sometimes recover your error here, right? Or at least undo that. This is another thing where sometimes when you do something, a computer will ask you, this will do this. Are you sure, right? And so by making you say, oh, am I sure? That means that this could be serious. And so therefore, I really need to think about that for a second. So it forces the user to stop and more carefully consider their action here. So having that kind of redundancy and barrier to errors and making people do things twice or to have to confirm their choices and things like that. I also list under here having a second operator, right? So here's a pretty unusual example. Extreme example is I guess the idea of launching a nuclear missile, right? You usually would have to have two operators, right? Each one gets their own key and they stand several feet apart so that one person could not do this. They each insert their key into a special, keyhole and turn them at the same time. And you can only launch the missile if those keys are both inserted and turned at the exact same time. And so that kind of is a prevention design, right? That prevents accidental or a lone operator who might want to launch a missile from being able to do so. I have other examples here. You may have heard of fail safe, but also there's fail closed. And so what is that? This implies there might be a fail open, which there is, but I just didn't get into this too much. But what happens if a system fails and there's some kind of an error that has occurred, and this is going to cause some kind of a system to fail? Uh, we can we do something to minimize the effects of that error? This comes up a lot of times in information security systems, right? That's what I mean by InfoSec. So, for example, if somebody tries to hack into a system, maybe we have a way of detecting that hack, and what we're going to do is we're going to automatically shut down the system as soon as we detect a hacking attempt. So a lot of security systems do that, right? You have certain like security systems where someone's trying to break into a building, and the security system detects the attempted break-in. Then this just activates all security systems. It shuts down a bunch of heavy steel doors and turns on alarms and basically just says, okay, we're going to close everything down. That's what that means, right? So in a network security setting, right, we just close the whole server and shut the whole server down to prevent any further damage. And somebody breaking into a fancy museum to steal an artwork, we just activate all security systems, lock everything down, shut the whole museum down. Locks work this way too. There are some locks, not all. If you try to pick a lock, there are some attempts at pick resistance that are designed to make the lock break itself, right? So when you try to pick a lock, if you don't know what you're doing, at least with these kinds of locks, the lock is designed to essentially break. And that means you will never be able to open that lock again, even with the key, right? You have to drill it out, right? And so that's a fail closed system as well. Basically saying, oh, somebody's trying to break into this lock and pick this lock. We're just going to, self-destruct, right? That will prevent, any more stealthy picking attempts, at least, right? A fail-safe is a way of trying to maintain safety in the face of failure, right? So we have a firewall. Now, a firewall historically is meant to be an actual wall that a fire will not burn through, right? So in case you're in a building and one part catches on fire, the presence of a firewall will prevent the fire from spreading to other systems, and this helps minimize the damage, right? Now, that term has been adopted in information security systems to talk about the idea that if someone hacks into a system, there can be a firewall that prevents them from getting too deep into more sensitive data, right? And so in that sense, again, the presence of that is a fail-safe, right? Even though the system was penetrated by a hacker, there's stuff that's still kept behind a firewall. That is, it's kept safe, right? Some other examples would be like a circuit breaker in a house, right? There can be an electrical failure and a short circuit that would cause a serious issue, but with a circuit breaker, it turns that circuit automatically off as soon as the fault is detected, and therefore that prevents anything bad from happening. Also, other examples would be any automatic safety systems, right? Airbags in cars are fail safes, right? Like we want to do as much as we can to prevent a person from crashing. But if the case that they still crash, then we have one last little thing to help keep people from dying, which is to have the airbags deploy as a fail safe. Hopefully that's going to help you, right? I listed here automatic braking systems, right? So trains, modern electric trains have auto braking systems. Elevators, in case the cables break, they have auto braking systems so that people don't just go falling down the shaft and so forth, right? So those are all fail safes, right? We don't hope and think that these things are going to happen, but just in case, we have a way of minimizing the negative consequences of that. Well, I mentioned these before, right? These are part of our prevention design. If we are going to delete something, it's going to be deleted immediately. Are you really sure? right? And if you've downloaded some executable file from the internet and you want to install or run it, maybe that's not so safe. And so again, the computer is going to say, hey, are you really sure you want to do that? Uh, and so those are different ways of prevention design, right? We're gonna try to prevent the user from making a mistake in this case. All right, well, that's enough about errors for this point, though we do have another part 2 coming up where we're going to talk about um, uh, uh, using automation to try to stop errors, which is related to what I said before about self-driving cars and exclusion design. But we'll save that for next time.